Okay, today we learn about inverse functions, which will lead us into the natural log function and the exponential function e to the x. Okay, so first up is finding out what an inverse function is. And to do this, we are going to graph two functions and compare the two functions together. So first off, we are starting off with the function f of x equals x squared, where its domain is x greater than or equal to 0. So the domain tells us what numbers to pick, and you can only pick from 0 to infinity, any large numbers. And lucky us, the XY chart is already made. So they are telling us to plug in 0, 1/3, 1/2, 1, 2, and 3 and square them. Okay, so we're plugging 0 in for x squared. We're plugging all the values in to x squared. So 0 squared is still 0. 1/3 squared gives me 1/9. And in decimal form, 1/9 is 0.11 repeating. So 0.11. And then 1/2 squared gives me 1/4, which is a quarter. And then 1 squared is 1, 2 squared is 4, 3 squared is 9. So those are the x and y values we will plot on this chart down below. Okay, so let's plot y equals x squared. We are at 0, 0, 1/3 and 0.11. So 1/3, so here's 1. So 1/3 and 0.11, that's going to be barely above 0. And then 1/2 and a quarter, same thing. At a half, we'll just go a little bit higher. And then 1, we're at 1. 2, we're at 4. And 3, we are at 9. There's 3, there's 9. So 3, we're at 9. So this is what our x squared function looks like that has a domain which is restricted to x greater than or equal to 0. Whoops. Want a more curvy. Let's see. There we go. So this is x squared. Okay, everybody good with that part? Good, good, good. Okay. Now, let's look at the function x to the 1/2, which we're going to plot on the same graph. So x to the 1/2 is essentially or the same as the square root of x. So all we are going to do now is take all of these values and plug them into x to the 1/2, or even better, it'll be easier to plug them into the square root of x. So when we do that, you will get the square root of 0, which is 0. You'll get the square root of 1/9, which gives me 1/3, which is 0.33. We'll get the square root of 1/4, which gives me 1/2, which gives me 0.5. And then the square root of 1 is 1. Square root of 4 is 2. And square root of 9 is 3. So let's go ahead and plot this on our graph as well. I should change the color though. Let me see. Let's make that all purple. This one. There we go. Okay. So we'll plot this on the chart, and 0, 0 right here. And then 1/9 will give me 0.33. Well, 1/9, remember, is 0.11. So 0.33, it'll put me somewhere right around there. 1/4 puts me at a half. So a quarter, I'm at a half. And then at 1, I get 1. And then at 4, we get 2. And then at 9, we get 3. So here's what the square root function looks like. So this is the square root of x, or x to the 1/2. Same thing. Okay. Now, to answer the questions below, we say, or just that question, sorry. This says, how are the x and y coordinates of the square function and the square root function related? So look at both of these XY charts and tell me if you notice any similarities.
They're both positive?
They're all positive. That's good. What else do you notice? Let's look at one coordinate to be exact. Let's look at an easy one. 2, 4. This is for x squared. Now, if we look at that same coordinate, you would have 4, 2. So in the square root function, you plug in 2, you get 4. In the squared function, you plug in 2, you get 4. In the square root function, you plug in 4, you get 2. Now look at all the other coordinates. What do you notice about them?
They follow a pattern. Everything is like the square root of it, or like it's
They
double,
seem
or
almost like symmetrical.
Good. We're getting somewhere. So there's a pattern. They're symmetrical. How about we just say something really easy? They're swapped. Look at this. 3, 3, 9 down here. 9, 3. This is 1, 1. You can't really see a swap on that, but that's still 1, 1. Now look at this. 1/4 and 0.5. Look at this. 0.5 and 1/4. So we see that for x squared and x to the 1/2, their x and y coordinates are both swapped. They have switched places. Okay, so to answer 3, it says, how are the x and y coordinates of the square function and the square root function related? We say that the x and y coordinates, ooh, can I type here? No, I can't. Okay. We say that the x, y coordinates are swapped. Or if you want a big fancy word, the x and y coordinates are interchanged. And yes, going along with inverses. So now, since these x and y coordinates are changed, we notice that this creates a type of symmetry on the graph. If you look at these two functions, they are symmetric about each other. So look at this. This point is 3, 9. This point is 9, 3. So one thing about inverses, if two functions are inverses of each other, then they are symmetrical about the line y equals x. So if you have two true inverses, they reflect across each other. So the same could be said for this point. This point is 2, 4. Flip it over that line y equals x. This point is 4, 2. So a couple of things happen with inverses. If they are true inverses of each other, your x and y values switch places. Graphically, if they are true inverses of each other, they reflect, or they are symmetric about the line y equals x. And then dealing with domain and range, it still deals with the way x and y are swapped. So the domain and range of one function, if you flip it around, becomes the range and the domain of the other function. So it's pretty cool. So this is what defines inverses. Don't worry, we'll get more to it on the next page, I believe. Oh, maybe not. So here, let me see. To be an inverse, let me write down everything I just said. So to be an inverse, your X, Y swap, your graph is symmetrical. So graphs are symmetrical. And the last thing is domain and range also swap. So those are the three things we know about inverses. One, if they are true inverses, your X and Y coordinates will swap. Your graphs will be symmetrical about the line Y equals X, and your domain and range will also swap. So I guess before I move from this page, let's look at the domain and range of the first function. So they're giving us the domain already. So this domain would be X greater than or equal to 0. And the range, well, this function can only start at 0 based on our graph. So this range would say Y is greater than or equal to 0. Now, if I put this into interval notation, this would be 0 to infinity. And this would also be 0 to infinity. So seeing the swap here is not going to be too complicated because even if we swap these, they're going to be the exact same. So when we look at the domain and range of X to the 1/2, the range of the inverse becomes the domain of the other function. So this means that you would have the domain 0 to infinity, and the range, well, the domain of the original function or the inverse will become the range of the other function. So, but in this case, it's not fun because our domain and range is exactly the same. Okay. So those are characteristics we look for when we get inverse functions. Okay. Everybody good with that page? Okay. All right. Next, B says to solve the equations. So on 4, we have X to the 1/2 equals 3. So X to the 1/2 equals 3. Now remember that X to the 1/2 can be rewritten as the square root of X equal to 3. Now, if I wanted to solve this equation and I wanted to solve for X, how would I get rid of this square root? What would I do to both sides?
Square it, like to the second power?
Good. So to get rid of that square root, you would square both sides. And the square root and the square, those would cancel and leave me with just X. And then 3 squared would be 9. Okay. And of course, the reason for the square root and the square to cancel, well, if we kept it in this form, X to the 1/2 equal to 3, and I squared both sides, well, you have this operation now, power to a power. So when you have a power raised to a power, the operation is multiplication. What is 1/2 times 2?
1.
1. And that's why that these powers would cancel and leave you with X equals 9. So that's why the square root raised to the second power would cancel. Okay. Now Let's try number 5. 5 has x squared equal to 9, and it's telling us that whatever answer we get has to be greater than 0. So in order to solve x squared equals 9, what would we do to both sides? What method would we use on this that we learned previously?
Square both. Oh, no, multiply.
You're close. We have to do, how do we get rid of that 2? What do we have to do?
Square root.
There you go, square root. And remember, when you square root something, you get x equals plus or minus, and the square root of 9 is 3. But our domain says we have to choose an answer that's greater than 0. So which answer are we going to go with? Positive 3. So we stay with just positive 3. Okay, so in the first one, number 4, you have to square both sides. On the second one, you square root both sides. Okay, everybody good with those 2? Okay. Now just a recap on inverse functions. What is the main idea behind inverse functions? Because then what is the relationship between x and y coordinates? How are the graph of inverse functions related? And how are the domain and range of inverse functions related? So what is the main idea behind inverse functions? Shoot, I don't even know that answer. What would we say? The main idea behind inverse functions. Or what would be another way to word that? We don't want to say that inverse functions are positive because that's the only examples we'd be given. Inverse functions can be negative. So the main, we'll skip that one for now. We'll go to the other 3. I'll think of it later. What is the relationship between x and y coordinates of the inverse functions? They are interchangeable. Or we like to say swap. And how are the graphs of inverse functions related? Well, we saw that they are symmetric. Okay. And how are the domain and range of inverse functions? Well, again, your domain and range are also interchangeable. Right here, I'm going to say skip. We'll think about this one later. Okay. So that's everything right now on inverse functions. So the main thing we look for is that the x and y values swap, the domain and range swap, and their graphs are symmetrical. Okay. Everybody good with this page? Okay. All right. Now let's get into 2 actual inverse functions that are important. The first one is the natural log of x, and the second one is the exponential function e to the x. These 2 functions are true inverses of each other, but let's go ahead and show that by using the XY charts again. Let's use the graphs, and then I'll show you a sweet little trick on how to interchange from logs to exponents and from exponents to logs. So let's work through this. Okay, and if you are typing this in on Desmos, that is an L, right? You would type in L N. It is not an I. Students make the common mistake of typing IN, and it's not going to do anything for you. That is the letter L. Okay. Okay, and of course, let's Desmos this. Boom, boom. And I'm going to type in Y equals E to the X. And then I'll create my XY chart. So once again, hit that little gear icon up there, click that, click the convert to table, and let's type in the values we're given. -3, -2, -1, 0, 1, 2. All right, and here's what we have. So at -3, we have 0, I'm going to round to 2 decimal places, 0.05. At -2, 0.14. At -1, 0.37. At 0, we get 1. At 1, we get 2.72. And at 2, we get 7.39. Okay. Now we can go ahead and graph this down below. So at -3, I'm at a nickel, so 0.05. So -3, we're like right here, barely above the x-axis. And then -2, we're at 0.14, not much higher. And then at -1, you're at positive 0.37, still not much higher. And then 0, you're at 1. 1, you're at 2.72, which I'll put really close to 3. And then at 2, you're at 7.39. So there's 7. So at 2, 7.39, we'll just put it close to 8. And here's what the exponential function e to the x looks like. So this is e to the x. Okay, now let's go ahead and graph the natural log of x. Okay, well, when you type this in Desmos, again, it's the letter L. You'll do ln of x. ln of x, just like it is. And you'll make your little XY chart again. So convert the table, and we will pick those values again. But what's great about this is that now we know that e to the x and the natural log are true inverses of each other. So we actually just have to look at the table we made above and do what with it?
Reverse it.
Reverse it, flip it, reverse it, swap it. So this means at 0.05, at 0.05, you'll get -3. At 0.14, you'll get -2, and then -1, and then 0, 1, 2. So again, we just take these coordinates, flip them around. And if you need to prove it, well, we'll just do it down here. So 0.05 gives me -2.995, which is -3. 0.14, and then 0.37, and then 1, 2.72, and 7.39. So in all of those, if you round up, you'll get -3, -2, -1, 0, 1, 2. Okay, so let's go ahead and plot those on our graph. And at 0.05, so here's 0, and 0.05 is going to be really close to the y-axis, and you go down to -3. So you're going to be just right to the right of the y-axis. And then at 0.14, you're at -2, so not much further to the right. And then at 0.37, you're at -1, so a little more to the right. And then at 1, you're at 0. At 2.72, you are at 1. So we'll put that close enough to 3 there. And then at 7.39, you are at 2. So we'll just put that around there. And here is what the natural log function looks like. And you'll follow that down and follow this out into the right. So here's the natural log of x. Okay, awesome. So first off, let's look at domain and range of e to the x. So remember that this is an exponential function. So the domain of all exponential functions is always -infinity to infinity. The range of all our exponential functions is 0 to infinity. Because if you look at e to the x, as this tail heads to the left, will it ever touch 0?
No.
No, it'll never touch 0. No matter how small x gets, you're never going to touch 0. Okay, now here's where we actually get to see a domain and range swap. So the domain of e to the x now becomes the range of the natural log of x. So the domain of e to the x now becomes the range of the natural log, -infinity to infinity. And now the range of e to the x becomes the domain of the natural log of x. So this is now 0 to infinity. And you can see that by the graphs. The natural log will never, ever touch 0. And if you look at my chart in Desmos, if you type 0 in to the natural log, you get undefined. So you can never, ever take the natural log of 0. So here's a good example where you get to see the x and y switch places, and you also see the domain and range switch places. The next thing we want to look at is the symmetry. Well, if I were to graph this line, y equals x, do these functions look symmetrical across this line?
Yes.
Yes. And again, you can prove it. Pull a point. This point is, what do we have? 2 point, no, this one is 2 and 7.39. And this point is 7.39 and 2. So we take that point, reflect it over that line. And you can see that these two graphs are symmetrical. Okay, and even better, using Desmos, it looks prettier. Nah, yeah, it looks, my drawing's prettier, but you get it. So using Desmos, if I click on this point and I click on that point, you see that these are definitely symmetrical across this line, y equals x. And you can click on any point you want. There it is, 1 and 2.71, and then 2.72 and 1, 0, 1, 1, 0, -3 and 0.05, 0.05, and -3. Okay, so now we have proven and we have shown that the natural log and the exponential function e to the x are true inverses of each other. Okay, so before we go to number 3, I'm going to show you a cool result of being an inverse. So let's start with the natural log. So let's do this over here. If you can, so here's the thing, if you can interchange domain and range, then you can interchange a log into an exponential, and you can interchange an exponential into a logarithm. So we'll just call this interchanging inverses. So let's start off with this function. We're going to say y equals the natural log of x. Okay, well, the natural log has a base of e. So if I were to rewrite this, I can rewrite this as y equals the natural log base e of x. So if you ever see the natural log, just know it always has a base of e. And this further proves that these two functions are true inverses of each other. So now what we're going to do here is we are going to go from natural log to the exponential function. So in order to do that, I take this base of e and I raise it to that outside number of y. So this becomes e to the y power equal to, and now I set e to the y equal to whatever's inside my parentheses. So I have e to the y equals x. And what we have just done is converted a natural log into an exponential function that has a base of e. So whenever you're interchanging logs to exponential, one thing you notice is that the base of the log becomes the base of the exponential function. So let's do an example real fast. Let's say I had y equals natural log 5. And if I wanted to convert this to exponential, so I'll put this example, I would rewrite this as natural y equals the natural log base e of 5. Now when I convert, I say base e raised to the y. So I have e to the y, and you set it equal to whatever's inside the log, and I'll say that's 5. Okay, so that's how you convert from log to exponential. So this is log to exponential. Now, let's look at converting from exponential to logarithm. So we're going to go now from exponential back to log. So I'm going to start with this function. Y equals e to the x. Okay. And now to convert from exponential to logarithm, well, the base of the exponential function becomes the base of the logarithm. So let me move over to the right. So we'll say natural log of base e of the outside number of y. So now we're going to get natural log base e of y and set this equal to that exponent of x. And if you ever need to check your work on this, just reverse the process. Convert it back from log to exponential. You would have base e raised to the x set equal to y. And if this function looks like your original function, we've done it correctly. Okay, so if you ever need to check your work, just reverse the process. Okay, but to finish this off, we know that e is the base of the natural log. So this finishes to just natural log y equal to x. You never, ever have to write that base of e when you are making calculations. You only put that base of e there when you are converting from exponential to log or log to exponential. But you get rid of it after you convert. So this is what we're going for. Okay, so example. let's say I have 10 equal to e to the x. Now, when I convert, the base of the exponential function becomes the base of my logarithm. So we'll have natural log base e of the outside number of 10 set equal to that exponent of x. And once again, we don't need that e there anymore. And our final answer would be natural log 10 equals x. There you go. All right, guys. And again, the reason we are able to do this is because they are inverses of each other. So that's how you go from log to exponential and exponential to logarithm. Don't worry, we're going to get more practice, I believe, on the next page. Okay. Everyone good so far?
Makes this stuff up.
Yes.
Some really, really old dudes make this stuff up.
Jeez.
I will tell you, though, that logs are amazing. So the reason logs were invented were to put these extremely large numbers, which are called transcendental numbers. They take these extremely large numbers and put them into a simpler format. And the greatest example I could give you is an earthquake. So whenever an earthquake hits, what does the news tell us? Oh, that was a 5. Oh, that was a 6. That was a 7 on the Richter scale. And we're like, oh, that must be bad. It was a 7. But we have no idea what goes on in the background of those calculations. So if you have a 7 on the Richter scale, you just shook a whole city, or maybe you shook a whole state. How large do you think that number actually is?
Chilling.
Super huge.
Really, really large, right? So what logs do is they just condense it into a smaller number for us humans to understand. So we're like, we'll take that 7. I don't want to see that it was 7 million or 7 billion millimeters. Just give me 7. So that's why logs are created. Logs are created to put things into a simpler format. Another example would be distance to a planet. We know distance to planets is millions of miles, billions of miles, but we're like, oh yeah, just put it into this and we'll just say it's 2 point something miles or whatever. So that's what logs do. They take extremely large numbers and put them into a simpler format. And truthfully, logs make algebra, calculus, any advanced math very easy. They make math really easy, but students decide to hate logs. It's beyond me, but showing you this probably makes you hate logs anyways. So I get it. I get it. Okay. So let's keep going. Okay. So next it says use a calculator to evaluate, give exact answers when possible, and round approximate answers to 2 decimal places. Okay. So here we get to use our calculator. Yeehaw.
Time out. Time out.
What's up?
Did you do number 3?
Did I always skip number 3? How are the x and y coordinates of these 2 functions related? Give the domain and range for each function. We gave the domain and range already. And again, since they're inverses, how are those x and y coordinates related?
They're interchangeable.
They're interchangeable. So there we go.
That it?
That's it. That's it.
Okay.
X and y are interchangeable. Okay. Sweet. Okay. All right. Now we just get to use a calculator here. I don't think I need graphs anymore. No. So I'm just going to use their regular scientific calculator. Leave there and then good old scientific. There we go. Okay. So here it wants the natural log of 1. All you have to do is type in ln of 1. And if you want, put parentheses for good habit. And the natural log of 1 is 0. Okay, and let's just continue this. Natural log of 8, and then natural log of 800, and then natural log of 8,000. Okay, so natural log of 1 is 0, natural log of 8 is 2.08, natural log of 800 is 6.68, and then natural log of 8,000 is 8.99. Okay, now to answer number 8, it says, how are the inputs changing in problem 4 through 7? So it says, how are the inputs changing? So it's the numbers we plugged in. So we plugged in 1, we plugged in 8, we plugged in 800, we plugged in 8,000. What's happening to our inputs?
Increasing.
Yeah. So we say inputs increasing. And now it says, how are the outputs changing in those 4 problems? So look at our outputs: 0, 2.08, 6.68, and 8.99. What's happening to our outputs?
Or doubling.
Not necessarily doubling, but they are kind of increasing as well, right? So we went from 0 to 2 to 6 to 8. So we can say outputs are increasing as well. But are they increasing at a smaller rate? Because look what we have: 1, 8, 800, 8,000, and then you have 0, 2, 6, 8. So definitely increasing at a very, very much smaller rate. So C, maybe I just answered that for C. It says, what is the difference between how the inputs are changing versus how the outputs are changing? I did answer that. So our inputs are getting increasingly large, right? While our outputs are increasing, but are the outputs a lot smaller than the inputs?
Yes.
Yeah. We're just going to say outputs smaller than inputs. Because remember what logs do. They take extremely large numbers and put them into a smaller format. So we're saying the natural log of 8,000 can be read as 8.99, which 8.99 is what? 1,000 times smaller than 8,000. So that's what's happening. The outputs are smaller than the inputs. Okay, everybody good with those? All right. So now next is to evaluate. Okay, so look at number 9. You have the square root of 3 squared. What do you think would happen to the square root and that square?
Go away.
Go away. What's a fancier term for go away?
We should
Cancel each other.
multiply it.
They cancel, right? So the square root of 3 squared, the square root and that square would cancel, and what number would I be left with?
3.
3.
That's it. All right. And if again you wanted to check your work, well, what's 3 squared?
9.
9. And what's the square root of 9?
3.
3. Look at that. Or we say that square root and that square cancel. Okay. Now, same situation here. Look at 10. Square root of 13 squared. What's going to happen again?
Just turns into 13.
It's just 13. Okay. Sweet. And now 11, 12, 13, and 14. Okay. So before we get into those, yes, I'll show you how to type them out on a calculator, but I'll show you an even easier way to work these without having to even use a calculator. So here are some log and exponential properties. So let's go here. I'm going to say log/exponential properties. Okay. So if you ever have, so I'll say property 1. If you ever have the natural log of e, so if you ever have the natural log of e, this will always cancel and become 1. So the natural log of e is 1. 2, if you have the natural log of e raised to any number, then the natural log and e will cancel and you'll be left with that number. All right. Am I taking care of these? Yeah, that would be for 12, 13, and then to get the properties for 11 and 14, if you ever have e raised to the natural log of x, the e and the natural log will cancel and leave you with just x. So these are some log and exponential properties. And again, the reason we have these properties is because these two are inverses of each other. So now let's look at number 11 over here on the left. E raised to the natural log of 7. Does that look like property 1, 2, or 3?
3.
3. So e to the natural log of 7, the e and the natural log would cancel, and what would I be left with?
7.
7. That's it. That's it. See how easy that is? Okay. Now, number 12. The natural log of e to the 5th. Does this look like 1, 2, or 3?
2.
2. So the natural log and e would cancel, and what would I be left with?
5.
5.
5. Good. What about 13? What would I be left with?
8.
8. And what about 14? What would I be left with?
15.
15. That's it. That's it. Okay. And again, you can prove these on the calculator. You can type these in if you want. I can say e raised to the natural log of 7, and you get 7. But why use a calculator now that you know these properties, right? I can even say natural log of e raised to the 8. And again, I get 8. Okay. Everybody good with those 6? Okay. Now let's get crazy. So I'm going to move that calculator there. Extend this here. I'm going to need some room. Because now we're going to be solving these equations. Okay. So on 15 through 20, identify the variable, then solve for the exact answer. Okay. So 15. I'll work them down here. There's more room here. So 15. We have 400 equals 50 times e to the k times 10. I'm just going to rewrite that as 10k. All right. So these instructions say identify the variable and solve for it. So in this equation, we are going to be solving for k. So in order to solve for k, we have to get k down from being an exponent. And the only way we're going to be able to do this is to rearrange this exponential function into a logarithm. So this is going to use this property. If we have y equals e to the x, then I'm going to have to rewrite it as the natural log base e of y equal to x, which remember translates into natural log y equals x. So our goal is to convert this equation using this property. Okay, so the first thing we're going to do on this equation is isolate e to the 10k. So in order to isolate that, I'm going to divide by 50. So let's divide by 50 on both sides. And what is 400 divided by 50?
8.
8. So you get 8 equals e to the 10k. Now we are in the perfect form to convert from exponential to logarithm. So when we do this, you're going to have the natural log of base e. So this becomes natural log base e of that outside number of 8 set equal to that exponent of 10k. Okay, guess what? 10k is no longer an exponent. We have rearranged from exponential to logarithm, and now I want to rewrite this without that base of e, and you get natural log 8 equals 10k. And now to solve for k, we just have to divide by what?
10.
10. There we go. Didn't want us to solve. Yep, solve for the exact answer. Okay, so now what we're going to do using the calculator is type in the natural log of 8 over 10. And we get that k will equal 0.2. Let's go to 3 decimal places. 0.208 is equal to k. There you go. All right. Everybody good with that one? It's a work in progress, right? Okay. Do it again for 16. 16 is natural log of 2x equal to 0. So 16 natural log of 2x equal to 0. Okay, so now this means we need to solve for x, but it's trapped inside the natural log. So this means we will convert from log to exponential. So now this is going to use the other property we learned. So if you have natural log x equals y, you rewrite this as natural log base e of x equal to y, and then you convert it. You say e raised to the y and set it equal to whatever's inside the parentheses. So e to the y equals x. That's exactly what we're going to do here for number 16. So let me rewrite this. I'm going to say natural log base e of 2x equal to 0. I now take base e, raise it to the 0th power. So I get e to the 0th. And then I set it equal to whatever is inside the parentheses, 2x. Okay, now we have a much simpler equation to solve. All we have to do is solve for x, so we will divide by what number? 2. We divide by 2. Does anybody know what e to the 0th is? Or what is anything raised to the 0th power?
Divine.
1. Good. So e to the 0th becomes 1. That becomes 1 over 2. And x equals 1/2. Not bad. Everybody go with that one. Right. All right. 17. Natural log x minus 2 equal to 1. So 17. Natural log x minus 2 equal to 1. We're going to do the exact same thing we did in 16. we're going to convert from log to exponential. So let me rewrite this as natural log base E of x minus 2 equal to 1. And somebody convert this for me. What should I write? E to the what power?
0.
First power
E to the first power
equals x minus 2.
equals x minus 2. There you go. All right. And e to the first is just e. So you have e equals x minus 2. So all we have to do is add what number over?
2.
And you get e plus 2 equal to x. Okay, this wanted an exact answer, so I'm just going to say e plus 2. And we get 4.718 equal to x. Okay. Everyone good with that? Okay. 18. Natural log of x minus 2 equal to 0. Okay. I'll just do that to the right of here. 18. Natural log x minus 2 equal to 0. Hey, this is exactly like 17. I'll do it again. Natural log base E of x minus 2 equal to 0. And somebody convert that for me.
E to the 0th power equals x minus 2.
There you go. E to the 0th equals x minus 2. And we learned earlier that e to the 0th is 1. And all you have to do is add 2 over. And what's our final answer?
X equals 3.
X equals 3. All right. That's not bad. Okay. 19. 50 equals P times E. Let me zoom in for that. What does that say? P times E to the 0.06 times 10. Why don't they just multiply those two numbers already? So, all right. So that's 19. $50 equals P times E to the 0.06 times 10. Let me just double check that one more time. 0.06 times 10. Okay, so for this one, we need to solve for P. So that means you will divide by all of this mess. But first, before we do that, what is 0.06 times 10?
0.6.
0.6. Now, to solve for P, we're going to divide by E to the 0.6. So in Desmos, I'm going to type it in just like I wrote it. 50 over E, raise that to the 0.6. And we will get that P is equal to 27.441. All right, cool. Everybody good with that? Good, we're going. Okay. All right, and then 25 equals 50 times e to the k times 7. $25 equals 50 times e to the k times 7, which I'm just going to write as 7k. 25, 50, e to the 7 times k. Okay, cool. So our job is going to be to solve for that 7k. So this is just going to be like we did for number 15. We're going to convert from exponential to logarithm. But the first thing we're going to do is get rid of that 50. And 25 over 50 gives me what?
1/2.
1/2. And you get 0.5 equals e to the 7k. Now let's convert. I should write that in blue. Hang on. 0.5 equals e to the 7k. Now let's convert to natural log, and that base of the exponential becomes the base of my natural log. And we say base e of 0.5 is equal to 7 times k. Okay. Now remember, we don't need that base of e in there. So we just rewrite it as natural log 0.5 equal to 7k. And then we divide by
7.
7. There we go. And we get natural log of 0.5 over 7. And our final answer is negative 0.099 equal to k. All right. Everybody good with 15 through 20? Hi.
Yes, the only thing I have a question
What's up?
on is can there be a coefficient before natural log or ln or just log?
Yeah. Yeah. You can have like
So what would it
5
look like
natural
before,
log
like the
2.
equation before you turn it?
Like before it's like 5
Before
natural
it's
log.
in natural log, like what would it look like with e, or what would it look like before there's an ln?
Nothing. You have to say it again.
Because you know how like we transfer them from like one thing to the other.
Mm-hmm.
So if there was a coefficient, if there's like on the one in red, if there was like a 5 before ln e y or whatever, like how would it transfer to like
We would have
the y equals e squared?
Gotcha. We would have to move it by another property, but that's not till the last section that we learn.
There's some homework on it that has.
But then you might have to divide it like we've been doing here before you convert.
Gotcha. Okay.
Yeah. Okay. All right. Let's see. 21. So solve and round to 2 decimal places. So it says if $1,000 is invested, how long will it take to double to 2,000 at 3% rate of interest compounded continuously? Okay, so if we're compounding continuously, what formula do we use?
A equals PE to the power of RT.
Good. So we use our best friend, PERT. Okay. Again, I'm going to need some room here. So let's see. I'll just bring in Desmos when we need it. Okay. I'm going to put 21 right here. Okay. So 21, we're going to use PERT. And we're saying that we invest $1,000. So the beginning amount is 1,000. And we want the final amount to double to 2,000. And we are given a rate of 3%. So 0.03. Okay. And it says how long. So this means that we are solving for time. Okay. So since we're using PERT, let's plug in everything that we know. It's going to be 2000 equal to 1000 times e to the r 0.03 times t. And now our goal is to solve for t. So since this is an exponential form, we have to convert to logarithm. So the first thing we're going to do is divide by this 1000. And then 2000 over 1000 would leave me with 2 equal to e to the 0.03 t. Okay, so now we are all set. We are ready to convert to natural log. So we're going to say base e, so the natural log base e of that outside number of 2 set equal to that exponent of 0.03 t. Okay, we have converted to log. So once again, we don't need that base of e in there. So you get natural log 2 equals 0.03 t. And now to solve for t, we just divide by 0.03. All right, and now Desmos. So typing that in, natural log 2 over 0.03. And we get that in order for our money to double, it's going to take 23.10 years. So for our money to double from 1,000 to 2,000 at 3% interest, it's going to take 23.10 years. Okay. Everyone good with that?
Yes.
All right. 22. Stan takes out an $800 student loan. In 3 years, after making no payments, but accruing interest continuously, he owes $1,100. What rate of interest is Stan being charged? So again, here we are accruing interest continuously. So again, we will use our best friend, PERT. But this time we are looking for the rate. So we are going to be solving for R. Okay. So let's get the breakdown. Let me zoom out here. No room to work. So let's see. Okay. So over here, 22. He takes out an $800 loan. The final amount is $1,100. And he took this loan out for 3 years. And we are looking for the rate. Okay. So again, we are going to use PERT. We're going to solve for R this time. So we plug in what we know. That is 1,100 equal to 800 times E to the R times T. Okay. First thing to do is divide by 800. And 1,100 over 800 gives me 1.375 equal to E to the 3R. Now we will convert again from exponential to log. So when we convert, there's that base E, natural log base E of the outside number of 1.375 set equal to the exponent of 3r. Okay, everything's nice and cleaned up. So just rewrite this as the natural log of 1.375 equal to 3r and divide by 3. Okay. And here you get natural log 1.375 over 3. And the rate that they are getting on this loan is 0.11. And it says since it's a percent, we want to convert from decimal to percent. So they are giving 11% on this loan. Okay. Everybody go with that?
Yep.
So once you start converting back and forth, exponential to log, log to exponential, yes, it takes practice, but once you get used to it, hopefully it becomes a little easier to work with. Okay. Last one, guys, 23. We have Jill wants to invest some money for her new nephew. She finds a CD that will pay 4.25% interest compounded continuously for the next 20 years. If she wants the future value of the CD to be $5,000, how much does she need to initially deposit? So again, we get to use our best friend, PERT. We are compounding continuously. So this is going to use PERT. Okay, but this time we are solving for the beginning amount. How much does she need to initially deposit? So we're going to be looking for P. Okay, so to make this simple, in order to solve for P, you're going to divide everything by ERT. So the formula we're going to be using here is A over ERT equal to P. So let's put everything that we know together. So 4.25% interest, I can squeeze that down here. So 23. So the final amount needs to be $5,000. We are doing this for 20 years, and the rate is 4.25%. So 0.0425, and we're looking for the beginning amount. Let me make sure I wrote all that down right. 5,000, and then 20 years, and then 0.0425. Okay, awesome. So now we just plug it into our formula. P equals A over ERT, and you get 5,000 over E raised to the 0.0425 times 20. Okay. Now type it in just like I wrote it. So we're going to say divide 5,000 over E raised to the 0.0425 times 20. So if they want to have that $5,000 in 20 years, they need to make an initial deposit of $2,137.07. Okay. All right, guys. Those were inverses of each other. So still need to figure out the answer to that other question of why this is important. Maybe because we can convert them into each other. We can figure out an easy way to solve. But we will learn more inverses on Monday. So on Monday, we will learn the common log and the exponential function 10 to the x. So we are done. So if you got questions, stick around. If not, see you on Monday.